So, welcome everyone to lecture number 13 in the lecture Statistical Theory for Deep Learning. We are in the middle, well, in the first part of the middle basically, of the chapter about neural network generalization, where I introduced some classical stuff from Wapnick-Sheremenko theory. And we just finished our first part of it, where I introduced two exponential inequalities which enabled us to bound the difference between average and the sample mean uniformly over some function space. And I made a few questions for the list of action questions out of this, which I would like to present first. And the new questions are, well, where is it? This is still approximation. We started, I think this was all approximation until 12. 13 is the definition of the LP epsilon covering number of f on Z1n. Then 14 is the proof of theorem 3.1 of the lecture. The theorem is formulated and given, and there's a hint where it's shown that what you have to show in step 1, step 2, step 3, and step 1, step 2, and step 3, and step 4. Well, okay, step 4, you have to remember yourself that you have to apply Hoeffding's inequality at that point to the inequality, so it's not on the hint here. And that's it. And then I didn't put the proof of theorem 3.2 on this list of excellent questions because it's much too complicated. Instead, I made something which you can get out of the proof and which you will show in the practicing course. It's question number 15. You let b be greater equal 0, you let x, y, x1, y1, and so on are d cross minus bb value general variables. You let f, let m be the corresponding regression function. You let f be a function from Rd to minus bb. Then you define z as f of x minus y squared minus f of x minus squared. And the first part, you have to show that the variance of z is bounded by 16b squared times expectation of z. So here you use the third binomial formula to write this a squared minus b squared as a minus b times a plus b. Then you get it. And then you show by applying, this is Bernstein's inequality, that the probability that the expectation of z minus 2 times the average of the zi greater epsilon is less than e to the power minus n epsilon divided by some constant times b squared. You will show this in the practicing course, and you will see how it goes. And then also you show part 3 in the epsilon course. With this you can analyze the least squares estimate if the set of function is finite. So calligraphic f is now a finite set of functions from Rd to minus bb. Mn is the corresponding least square estimate, then the expected L2 error is less than constant times log number of sets in Fn divided by n plus 2 times the approximation error, the minimum f and Fn of f of x minus m of x squared integrated with respect to distribution of x. And there is no hint here, but you will see a hint in the practicing course, and then you have to remember the trick. So this is what we did in the lecture, that you write L2 error as the L2 risk of the regression function minus the L2 risk of the estimate minus the L2 risk of the regression function, and you subtract 2 times its empirical value. So 2 times the empirical L2 risk of the regression function minus the empirical L2 risk of the estimate minus the empirical L2 risk of the regression function plus 2 times this term, and the expectation of 2 times this term is just the second part here, as you can easily show from the definition of the least square estimate, and then you have to apply part B together with the union bound to get a bound on the probability that the first term is greater than some t, and you bound the expectation of the first term by the integral from 0 to infinity of the probability that its first term is greater than 0. Okay, And now you have seen what we have done. I can show you again theorem 3.1, for instance, and we had another version of it, theorem 3.2, where we bound the supremum over some g in the function space of the sample average of the g of zi minus its expectation uniformly over this function space. We get some exponential term which goes down exponentially in n, but in front there is an expectation of some L1 covering number. So in order to apply this to analyze estimates, we need bounds on the covering numbers, and that's what we introduce next. And I haven't uploaded yet this latest list of excellent questions, but we'll do so today. Okay, that's it. Any questions? So the idea is we need to bound this covering number, and that's what the next section is about. 3.3 covering numbers in PC dimension. So I will introduce a new term, the VC dimension, new definition, and with this we will prove some theorems which helps us bounding the covering number. Before I do this, well, the covering number is something like you have a set, you look at how many balls of some radius you need to cover the set. And this is related to the number of points which you can find in the set which have some distance. And that's our second term, or second definition which we need here. It's a so-called packing member. That's definition 3.2. And I start like as I started with the definition of the covering number 3.1. You will have some radius which is an epsilon greater 0. You have some set of functions calligraphic G. Here a set of functions. Reduce here RL. I have some p between 1 and infinity, and less than infinity, because I will define a p norm. And I have a probability measure mu on RL. Then I define the LP nu norm of the function g in the usually way. G to R. Measurable, of course, set this norm. G nu. You look at the integral of absolute value of g of x with exponent p, integrated with respect to mu, and takes the p's root out of it. So it's integral over g of x, exponent p, mu dx, and we will be in particular interested in p equal 1, L1 norm, and we will be particularly interested in case that mu is the empirical distribution to some points x1 to xn. So in that case, this whole guy will just be the arithmetic mean of g of absolute value of g of xi. And the first thing which I define is an epsilon packing, and that's a finite set of functions, and an epsilon packing of g, a finite set of functions in g which have distance at least epsilon, pairwise distance at least epsilon with respect to this norm. So a finite set of functions and I denote them by g1 to gn, capital N, g. What's the property that the distance between gi and gj in our norm, this distance is always greater or equal than epsilon for all I not equal j. So for all 1 less equal I less equal j less equal n. And of course I can assume without the generality that I is less equal than j here. So any such finite set of functions is called an LP. No, it's called an epsilon packing of g with respect to our norm. Epsilon packing g with respect to our norm. And then we define the epsilon packing number of g with respect to this norm as the maximal number of functions in g which are an epsilon packing of g. So the maximum number of functions which have pairwise a distance at least epsilon. The epsilon packing number of g with respect to our norm and for this I use the notation m, epsilon g and the norm. Is defined as the cardinality of the largest epsilon packing of g. Epsilon packing g with respect to and of course, it might be that you can find infinitely many points which in the set, these points are in the set, which are at pairwise distance at least epsilon, then you set this packing number just to infinity. So here we set epsilon g u1 infinity if for every n there exists an epsilon packing of G which contains n elements. There exists. G is equal to which contains n elements. And now I do what we really need, and that's the LP epsilon packing number of G on some set of points, and that's just the LP. It's just the epsilon packing number of G with respect to LP of nu, where nu is the empirical distribution to these points. So the LP epsilon packing number, and I make another batch. Yes. Z1n. It's defined by, and for this I use the notation m with index p epsilon g in the points, and I use the m epsilon g with respect to the empirical distribution nu n of the points Z1n. Where nu n denotes the empirical corresponding to Z1n, and Z1n is a vector of n points Z1 to Zn. And each of these points Z1 to Zn is an R with exponent L, and you have n of them. And of course, I can also define an LP epsilon packing of G on Z1n, which just means that it's a finite set of functions G1 to G capital N, where this empirical P norm is greater or equal to epsilon for all I not equal to G. And of course, I could also define it easier if I could forget about A and B and directly define, or I could define B only, or A and B only in the special case that you have mu equal to mu n. Doesn't help much that we use here this probability measure instead. Okay. And maybe you see that there's a connection between these packings and these coverings. One nice property of these packings is that as soon as you have a packing, you know the centers, so these functions are in the function space. And if you have a covering, then you don't know that the functions, the centers of these balls with the covers are in the function space. Okay, and now comes the first rather simple lemma, which shows the connection between both terms. We have epsilon greater 0, g is set of functions as before, p greater equal 1, and u a probability measure. Then we have for any epsilon greater 0, I can bound what I'm interested in, leave a little bit space here and I write this one in the middle. I'm interested in the covering number, epsilon, g, and the norm. And I want to give an upper bound by some packing number, and I want to give some lower bound by some packing number. And the upper bound is the covering packing number with some radius, and the lower bound is a packing number with some radius. Now the question is, what are the radius which I have to enter in? Any idea? How can you bound the packing number by a covering number, and how can you bound the covering number by a packing number? So for the covering, you looked at some function g1 to gn, where for each function in the z, the distance to one of them is less than epsilon. Any idea? Of course, it's in the lecture notes, but maybe if you don't look in the lecture notes, then you can think about it yourself. Well, I could write 0 here and infinity here, which is not defined here, on the other hand. But no, I have to write 0 here and infinity here. Yeah? So that is not so easy. But what you can enter here are some multiples constant times epsilon. And then it goes. Any idea?
Not yet 100% certain, but I think if we have an epsilon covering, it is also an epsilon packing.
If you have an epsilon covering, it is also an epsilon packing.
Or a minimal epsilon covering, rather.
If you have a minimal epsilon covering, it's a epsilon packing, because if you add one more point, then it's no longer an epsilon packing, which means that the point must be in some of the balls. It's a good point here. And where do you want to enter an epsilon because of this? On the left side or on the right side?
On the
on the right side. You want to enter epsilon on the right side. Okay, then we make a proof. And you told me already how to prove this, yeah? The first part. Then we think about the second part. So you told me that you want to have an... Well, of course, the assertion is trivial if this packing number is infinity. So without loss of terminology, we can assume that it's finite. So then we have a G1 to G capital N and G. G1 to capital N and G. Be epsilon packing of G with respect to the norm of maximal size. With respect to maximal size. And what you want to, this implicitly assumes already that this packing number is not infinity, but that's trivial. Yeah? It's infinity, it's trivial, you won't say. Okay. And now what you claim is that this is also an epsilon packing of G. Then G1 to Gn. Also epsilon covering G with respect to mu. And now we have to argue that, yeah? And for that we have to show that if you take an arbitrary G, small g from calligraphic G, then it's within distance epsilon of one of them. Distance less than epsilon of one of the G1. Because for any G and G. And now we need how to show this.
So if the G that I take is one of the n many that I chose for my packing, and it's trivial, and if not, then since it was a packing of maximal size, the distance cannot be more than epsilon, so it has to be less than epsilon.
The distance cannot be more than epsilon to all of the G1 to Gn or to some of the G.
No, there exists one of those n many GI, so that the distance is less than epsilon, and yeah, that's so it is satisfied that.
So you have to add G is not equal to J or J equal 1 to n. Then this, if you look at G1 to Gn, and addition G, in G, and these are functions in G, and these are now n plus 1 function in G, cannot be epsilon packing of G. Now this means that this condition here must be violated. So you find two different functions in these n plus 1 functions which have a distance less than epsilon. Since the first n has pairwise distance greater or equal to epsilon, there exists some j's at the gj and g. Yeah. Exists J1 to n satisfying. If I look at the distance between G and Gj, P of u, this must be less than epsilon. And that's it. And then you see this proves that this n epsilon so G of nu is less equal n, and that was by our assumption m epsilon G. So we have the first part. Great. Questions? Any questions? Now, what about the second part? What do we have to add here? What we did here, we used the packing and constructed from this recovery. Yeah? And this consideration does not help us for inequality, sorry for that. But any idea? And actually it's the easier part of the proof. But somehow you want to show if I have a packing, then my covering needs a lot of balls. And the way to do it is to construct a packing such that in each of the ball there is at most one function of the packing. Because this function in the packing, they have a distance. Now the question is, what kind of distance do you need? To achieve that in one ball of radius epsilon, there is at most one of the points.
Should be 2 epsilon.
Should be 2 epsilon. So how to formulate this? Well, you have a packing. Again, the G1 to Gn be an epsilon. G1 to Gn G be an epsilon. Be an epsilon packing. G with respect to norm. Then any ball of radius epsilon, oh no, but it's a 2 epsilon. Sorry. Clear mistake. Then any ball of radius epsilon can contain at least one of the G1 to Gn. Epsilon. contain at least one of them, at most, one of the G1 to Gn. And that implies that n is a lower bound for the covering number. And that implies also that the maximal size of the covering is a lower bound of the covering number. And that's it. Okay, questions?
It's again 2 epsilon.
Thank you. Same arrow again. It must be a 2 epsilon. So you see, as long as you ignore this factor 2 for the radius, it doesn't matter whether you bound a packing number or a covering number. And it will turn out that this dependence of the packing number or the covering number on the radius epsilon is not so strong, so we will ignore this factor 2. So in order to derive bounds on the covering numbers, we will use our main theorem will be a bound on the packing number. Okay, any questions so far? Then give me 5 minutes for cleaning the blackboard. We have now 10:26, so I go on in 10:31. Thank you. Okay, I would like to go on. We learned now that we can look at packing numbers and derive our bound for packing numbers, but before that I will need some additional definition, and in order to motivate this definition I will look again at covering numbers, but at covering numbers for set of indicator functions. So let me look at two indicator functions. Let f be the indicator of some za, so the function which is 1 if the argument is an a and 0 else. Let g be the set of indicator of some zb for ab subsets of Rd. And then I take n points, Z1 to Zn from Rd. And then I look at the LP nu n distance between f and g. The nu n is the imperial distribution to the Z1 to Zn, which means that you look at 1 over n, so your integral becomes a sum. F of Zi minus g of Zi is exponent p, and the whole thing with exponent 1 divided by p. And I want to construct it, and I will consider a set of indicator functions and will use indicator functions to construct a LP epsilon cover on Z1n. Now, of course, you can bound this one by if you bound the sum by the maximal term occurring in the sum, then you get another bound. Then you have the maximum of the p of the values with exponent p, which is the maximum of the values with exponent p, so the p and the 1 over p cancels, so the whole thing is less or equal than maximum I equal 1 to n. F of Zi minus g of Zi. And now if you consider the function values f of Zi minus g of Zi, both are indicator functions, so the function value is either 0 or 1, so the maximum will be 0 or 1. And you see it's 1 if you find some Zi in Z1 to Zn, which is in one of the sets, not the other. So if A intersected with Z1 to Zn is not the same as B intersected with Z1 to Zn, but if for any Z1 to Zn the point is in A, if and only if it's also in B, then it's 0. So 0 if A intersected with Zn is equal to B intersected with Zn. And now I can use this to construct the covering, because this implies consequently if you set G with a set of indicator functions, then here is a 1. Interesting, okay. I sometimes write 1, sometimes I write indicator I for the indicator function, it's the same. And in some set of calligraphic set. For a subset of V. Then I can make the following bound for any epsilon greater 0. If I look at the LP epsilon covering number of my set G on my point Z1n, then I can construct such a covering in a special way such that I choose my covering as indicator functions, and I choose them such that all possible values of one Z A in calligraphic A intersected with Z1, Zn occurs here. So I just use all these sets which occur here as possible sets for B, which means that the whole thing is less than the number of sets. A which means that somehow if you look at this set of sets and you want to measure its complexity in the way that you measure the epsilon covering number with respect to points Z1n of the set, then the set of set is not important. Important is only how the set looks if you intersect them with the endpoints, which is a much easier property. Questions? And to realize this was the first major contribution of Babnik and Chervonenkis, two Russian mathematicians, and this gives us definition 3.3. Ready to study this quantity? And I will define the shatter coefficient. So we are in the setting that we just had. We had A be a class of sets, A be a class of sets, A subset from RD. Then I have a natural number. And for points Z1 to Zn in RD, I look at this quantity on the right, which we just had, or upper bound on the covering number, and I denote this by S A and the points Z1 to Zn. And that's just the cardinality of A intersected with Z1 to Zn. A in my set calligraphic A. And this is the number of subsets of Z1 to Zn which can be picked out by sets in calligraphic A. Picked out in the way that you intersect with some of the sets, these points. So this describes perhaps the number of subsets which can be picked out by sets from A. And you see the connection with covering numbers, yeah? There's a connection here, connection with covering numbers of a set of indicator functions. Now you also see this, or can you give me an upper and a lower bound for this set, for this number? Well, lower bound will be -1, but maybe you have a better one. And what about an upper bound?
Most n factorial.
N factorial? N factorial. Okay, at most, let me give you some hint, the number of subsets of an endpoint set which you have here.
Yeah, it's at most 2 to the power of n.
It's at most 2 to the power n, yeah? And at least?
At least 1.
At least 1. It is some value between 1 and 2 to the power n, yeah? And we say that A shutters some set G if each subset of G can be picked out by sets of A. So if you have SAG is 2 to the power absolute value, number of elements in G. That's the second definition. B. That G you find it, that's the normal, yeah, but my normal G looks like this. We find it subset of B. We say that A shatters. Shatters G. S A G is equal to 2 to the power number of elements in G. Which means that each subset of G can be written in the form A intersected with G. Can be represented. A intersected with G. For some A element. Second part of my definition. And now my third part of the definition. Later on we have to bound covering numbers for some random Z1 to Zn, and the randomness might be a problem. We forgot about the randomness if we just look at the worst case. So we look at the maximum of this quantity for endpoints. And that's the shatter coefficient. See, the nth shatter coefficient of A and that's how I denote by S into n, and that's the maximum number of endpoints. So it's the maximum set 1 to let n be ID of S in 1%. So this one, that's the maximum number of different subsets of n points that can be picked out by n. It's the maximum number of different subsets of n points that can be picked out. Okay, somehow trivial, but on the other hand, not so easy to understand what it's really doing. So let us look at some examples. We will also be interested in how this function behaves as a function of n. Yeah? And we have already seen it's at least 1, at most 2 to the power n. Yeah? Because this one is at least 1, was 2 to the power n, so this one is at least 1. So example 7. Let me look at the subset of all intervals. Of all intervals minus infinity up to some right bound a, and including this right bound where a is 1. And what kind of sets does this set A shatter? Can you give me any finite subset which is shattered like this? Besides, and of course, basically not, we will not consider the empty set otherwise. Or can you give me any set which is not shattered? Okay, maybe someone else? Please?
I think if we have a set with 2 distinct elements, it's not shared.
If you have a set with 2 distinct elements, it's not shared, that's correct. Why?
Because we cannot choose the higher one.
Because you cannot choose the higher one, you can choose the higher one, but you cannot choose the higher one alone, yeah? Bigger one alone, yeah? If you have 2 sets, yeah? 2 points, yeah? One is then is the bigger one. You want the bigger one alone, not the smaller one. But if the bigger one is in, then A is greater than equal to the bigger one, then the smaller one is 3. So a set of 2 points is never shattered. Yeah? And also a set of more of 2 points. What about sets of 1 point? Is this shared? Yeah, always without problems. Yeah, you can, because you can get an empty subset by just choosing A less than the point, or just a point by just using A quadrant. So A shatters all subsets of R of cardinality 1. but it fails to shatter any subset. To shatter any subset. Of cardinality. Since it fails to pick out only the larger of two numbers. Okay, that was easy. Question? Then, make it a little bit more complicated. Let's look at the finite intervals of finite lengths. So B, I made the A bar, and that's the set of all intervals from A to B, where A, B is in R. What can you say about it, Mark? Please.
Every element that has a cardinality at most 2. Because at 3 we need to have the left one and the right one, but not the one in the middle.
Okay, that's the correct argument for the lemma which you did not tell, yeah? Or the assertion you didn't tell. What's your assertion? What do you want to show? The argument before it was right, but you didn't tell what you show, yeah? It shadows something and shadows something else not, yeah? So it shadows, which one does it shadow?
Subsets that are have the cardinality less than 2. 2 and less.
Yeah, A shadows, A bar shadows all subsets of cardinality at most 2, right? First point. And you easily see it, yeah? If you have 2 points, what can you do? Well, you can of course use an interval from here to here to just pick out the left one. You can use an interval from here to here, just pick out the right one, or you can use an interval going over both, or you can use an interval getting none of them, yeah? So we have all subsets here. That was the first part, and the second part? Did you already given a reason for?
If we have 3 elements, then we can't have a set where only the left one and the right one is in it, but not the one in the middle.
But it fails to shatter any subset of cardinality 3. Correct? Cardinality 3. Okay, that equals 3. because you cannot pick out the middle one of 3 points. Now, third example, I consider the set of all half spaces in R2. And I want to choose suitable points, number of suitable points, but it shatters numbers written here then. Currently chosen points in R2. And you should give me a number which is as large as possible. 1, 2, 3, 4, 5, 6, 7.
I think 3 if they are not in a line.
3, yeah, not in a line.
Actually, it also does not shatter any 4 points.
We make 3. And now, what does it mean to shatter? What is a half space? Half space means that I make a line through it, yeah, and half of the part I use. And how many subsets do you have? It's 8 here. So what are the 8 lines?
So first of all, I'm going to draw one where all of them are on the right.
All of them are on the right.
Then should I just tell you the 8 lines?
Yes.
Okay, so then I'm going to separate the top one, maybe. Yeah. The left one,
The left one, the right one.
Yeah.
The top one, the left one. The right one. Now we need all. We have these sets of cardinal subsets of cardinal 1, but at the same time we also get a subset of cardinal 2 if we just make the complement of the half space, yeah. And we have the set of subsets of cardinal 3, but we get also the 0 if we just make the complement, yeah. So you have all. Okay. So I don't add the upper few. Then finally, I consider the set of all convex sets in R2. I want to have the same question as before. That is, how many suitable chosen points Any idea?
Also again 3.
Again 3? What about 4?
Pretty sure we can't separate 4 with the same argument that we can't separate 4 with.
Okay, wait. I can make a convex whole of any of subsets of these and get exactly convex set which contains exactly these convex whole.
But if 4 of the points are on the line, then you can't.
Suitably chosen. I look at the best case, or the worst bound you get for a covering number here. exactly. And then, for instance, you make the convex combination of these three, yeah, and then you see it's a convex set, yeah, and it picks out exactly these 3 points here for any angle. So you see, it's totally different what you can get, yeah. Might be that you can get all, might be that you can get only a few. And I promised you to finish 14 minutes early. So we are close to this 14 minutes early, but not. So maybe I can make an, what is it called? Teaser for the next lecture, what we actually will show. We will look at the shatter coefficient and investigate how it behaves as a function of n. And it will turn out, and that was the major contribution of Wapnick and Scherban-Neunkvist to show this, or also to get this idea. It turns out there are 2 possible cases. Either the shatter coefficient is 2 to the power n for all n. That's, for instance, for the set of n points here. 2 to the power n for all n. Or if this is not the case, then it grows in n at most polynomial. But there's nothing in between. Either polynomial or 2 to the power n. And that's nice, because if you have a polynomial and if you look at our bounds for the covering number, then you have this bound on the covering number in front of some exponent term going down exponentially in n. And if it's polynomial, then you can forget about it. It's not important. Okay, any questions? So then I give you 15 minutes back, and I will increase the. Of course, I get some interest on this 1 minute, yeah, for the rest of the term. Yeah? It's clear. Okay, thank you very much. We have today Monday, so see you again on Wednesday.